Judges, this is Yatayat Niyantran, an AI copilot for event traffic command centers. The problem statement was event driven congestion. Rallies, festivals, construction, sudden gatherings all cause localized traffic breakdowns. And today, three things are broken. Impact isn't quantified in advance. Deployment is experience driven, and there's no post event learning loop. Everything you're about to see was built to directly answer those three gaps, drained end to end on 8,173 real Bengaluru Astram event records. Here's the approach end to end. I took 8,173 real Astram event records cause, corridor, zone, priority, vehicle type, timestamps, GPS coordinates, resolution times, road closure flags, and built four separate models, each targeting a distinct outcome instead of one black box trying to do everything. First, a congestion severity index, a transparent, rule based formula combining cause severity, road closure, peak hour timing, and priority. Scored in real time by a stacked ensemble of CatBoost and LightGBM, blended through an XGBoost meta learner. Second, the duration model, the one I'm proudest of. I engineered rolling spatio-temporal features. How many incidents hit this corridor in the last 1, 6, and 24 hours? And the historical average resolution time for this exact cause and corridor combination. I log transformed the duration target because it's heavily skewed, trained CatBoost on it, and critically trackbot split the data by time, not randomly. So the model is only ever tested on events that happened after its training window. Then I layered quantile regression on top, so instead of one number, the operator gets a P50 to P90 range. Third, an independent road closure risk classifier. CatBoost again, but predicting a completely different, genuinely observed target. Will this event require shutting down a road? Evaluated on AUC, with the decision threshold tuned against the precision recall curve instead of just defaulting to 0.5. Fourth, a manpower and routing layer. Officer and barricade recommendations visualized on a live deployment map and a road network diversion engine built on a real OSMNX graph of Bengaluru, with every edge weighted by local risk via a KD tree spatial lookup so it can compute a traffic aware route, not just the shortest one, and tying all four together. A post event feedback loop so the system doesn't just predict once and stop. It's built to keep learning from what actually happened. I'll show you exactly how each of these works on screen, starting with how an operator uses it in the moment. Here's the full pipeline in one view. Event parameters, location, priority time, crowd size, flow into feature engineering, grid binning, cause severity lookup, label encoding. That feeds the core ML models, our CatBoost LightGBM ensemble, and the CatBoost regressor. From there, the traffic aware diversion router kicks in using a live OSMNX graph of Bengaluru, and all four outputs lens simultaneously: risk heat map, manpower and barricades, route comparison, and economic impact. One input, four coordinated outputs, single deployed container. Start here. A command center operator logs a new event as it's reported: event cause, type, corridor, zone, priority, vehicle type, and two sliders for crowd size and expected delay. I'll set this to a heavy vehicle breakdown on Tumkur Road, high priority, evening peak. 6 pm, the worst possible time for that corridor. Clicking, run prediction, and the system responds instantly with 8 numbers, not one. Congestion at 41%, risk score 41 out of 100. Then the operational ask, 18 officers, 3 barricade points. Duration is 52 minutes with that 50 to 90 peso range I just described, showing 33 to 92 minutes. Road closure risk, low, at a calibrated probability of 0.485. That's the independent classifier firing, not derived from the congestion score. And the business case, this plan saves an estimated 1,072,500 rupees versus an unmanaged response. And it doesn't stop at numbers. Scroll down and you get a live map. Red pin is the event hotspot. The inner cyan ring shows where 11 officers go. The outer orange ring is 7 more officers on the perimeter. The 3 orange markers are the recommended barricade points. This is fully interactive. Zoom and pan like any map, and every marker is clickable for its own pop-up with the exact deployment number. Clicking refresh heat map button. This is the city-wide view, built from all 8,173 real incidents plotted on a live OpenStreetMap base layer. Clicking or zoom control twice on the map, red and orange show the highest density risk corridors across Bengaluru. And this is fully interactive. The numbered green and yellow circles are marker clusters. Clicking a numbered cluster marker, for example the 23 cluster, clicking any cluster and it expands to show the individual incidents underneath. Each one with its own pop-up showing the event cause and exact risk score. Zoom in further and clusters keep splitting down to individual red dots, so a commander can go from a city-wide pattern all the way down to one incident without leaving the map. And it refreshes live against the current dataset. Click Road Network Diversion tab. This is the routing engine. We build a live OSMNext road graph of Bengaluru and weight every edge by local congestion risk using a KD tree spatial join. Default route here is Mysore Road to the city center. But these fields are editable. Type any 2 coordinates in Bengaluru and recompute. Clicking Generate Diversion Route. The cyan line is the AI optimum route, traffic aware. The red dashed line is the plain shortest distance route, the one most GPS apps would give you by default. And the system quantifies the trade-off directly. AI optimum route, 12.27 kilometers. Average risk, 25.5 out of 100. Shortest route, 12.24 kilometers. Average risk, 27.2. Net result, 6.2% less congestion exposure for 30 extra meters of travel. That's the kind of trade-off a commander can approve in 2 seconds because it's already quantified. The map itself is fully pannable and zoomable, same as the heat map. Clicking Post-Event Learning tab. And this is the answer to the third gap in the problem statement. No post-event learning system. After an event resolves, an operator logs what actually happened. Actual congestion, actual officers deployed, actual duration. Real ground truth, not a prediction. Clicking Log this outcome. That appends straight to a structured feedback log. You can see it confirms the running count. These records are designed to be merged back into the training dataset. So, the model's understanding of what a procession on Magadi Road actually costs keeps sharpening with every real event handled, instead of staying frozen at the moment we deployed it. This is the loop most traffic ops tools never close. Predict once, never check yourself again. We build a mechanism to check every time. Clicking Model Performance tab. Now, the part most demos skip and the part judges should care about most. Are these numbers actually earned or just dressed up? This table is deliberately honest. The congestion index scores near perfect, R squared 0.9987, because it's learning a noun formula, and I say that plainly rather than hide it. The real test is the row below. With a random split, duration shows R squared of 0.52. But that's leaking future patterns into training. My time-based split drops it to 0.111. That drop is proof the baseline was inflated, not a failure. At this sample size, MAE and RMSE are the metrics that matter, and closing that gap is exactly what the feedback loop is for. The closure classifier sits at AUC 0.821, completely independent of the congestion formula. Every chart in this app expands on click for a closer look. And we don't stop at scores. Every model exposes its own feature importances. For congestion, priority and cause severity dominate, exactly what you'd expect operationally. For road closures, it's a different ranking entirely. Location, vehicle type, and corridor matter most. Different models, learning different signals, both explainable, not black boxes. And the raw data itself. Incident distribution by cause, average congestion by hour of day. Both expandable, both drawn straight from the real This is the publicly deployed space on Hugging Space that you can check without installing anything. This is also another publicly deployed image on Docker. For more details of how to use this Docker image, go through the description provided. The commands are directly given there.